Welcome back to The Explainer. This one is brought to you by Forge College. I'm your host, and today, well, we're basically rolling up our sleeves and putting on our master mechanics overalls. So grab your wrenches because we are diving into gas optimization patterns. We're going to take a real close look under the hood and get your smart contracts running like well-oiled, high-performance machines.
Now, in our last session together, we tackled designing modular function groups. You put in the work, you organized everything beautifully, and honestly, it looks incredible. But here is the multi-million-dollar question. Why does your beautifully organized code cost an absolute fortune to run? Well, just because your engine looks pretty on the outside, it doesn't mean it's not an absolute gas guzzler under the hood, right? Sometimes the most logically organized code is actually incredibly inefficient for the blockchain to process.
Okay, let's dive into this. Here is our literal engineering blueprint for today's tune-up. First, we'll look at the gas guzzler problem, then setting up diagnostics. After that, we'll be tuning storage and loops, optimizing memory and math, and finally, verifying the diagnostic report.
So, Section 1, the gas guzzler problem. We're popping the hood on expensive operations.
It's time to identify the heavy, inefficient mechanical parts that are really dragging our engine down. Whenever your smart contract interacts with the blockchain's permanent storage, it uses operations called sload to read and SSTORE to write. You can think of these as the absolute heaviest, most grueling mechanical lifting your contract does. I mean, a single SSTORE that flips a value, that can cost you tens of thousands of gas units. If you're doing this repeatedly, your users are paying exorbitant transaction fees just to run basic functions. These heavy storage operations are literally the primary enemy of a cheap, efficient transaction.
Moving right along to Section 2, setting up your diagnostics, basically plugging in the scanner.
Look, a good master mechanic never just guesses, right? They measure. So we need to set up our Hardhat gas reporter. To do this correctly, we're going to use a really tight 4-step diagnostic cycle. Step 1, measure the baseline gas. Just run a local test and see what the function costs right now. Step 2, identify hotspots. Find the specific lines of code that are burning the most fuel. Step 3, apply a single, targeted change. Don't change 10 things at once, or you'll have no idea what actually fixed the problem. And Step 4, remeasure and document the delta. We're going to use this exact cycle to systematically tune our contract and create a reliable debug report.
Which brings us to Section 3, tuning storage and loops, or as I like to call it, replacing heavy parts.
Now, what's really interesting about this slide is our first broken part. Let's look at a hypothetical function we'll call batch increment. The massive total gas-draining mistake here is reading and writing to storage on every single iteration of a loop. If you update a storage balance every time, you trigger that massive SSTORE fee over and over again. The solution? It's the highly efficient read-modify-write pattern. You just read the state into a local memory variable once, do all your math inside that cheap local memory, and then perform one single SSTORE right at the very end. The gas savings you get here are just absolutely phenomenal.
And while we're inside that loop, here is a brilliant little trick. In Solidity, math operations automatically check for overflows or underflows, which of course costs gas. But if we have a simple loop counter, let's say I, and we know for an absolute mathematical certainty that it is not going to overflow its maximum bounds, we can actually wrap the increment in an unchecked blot. That completely strips away the compiler's safety checks, which you didn't need anyway, saving you precious gas on every single loop iteration.
All right, Section 4, optimizing memory and math, swapping in carbon fiber. Shifting our focus over to data locations and pure computations, let's examine a helper function we'll call compute something. When passing external arrays into a function, you actually have a choice. Copying an external array into memory costs unnecessary gas. So instead, leave the array as calldata. Calldata is like lightweight carbon fiber. It's read-only, non-modifiable data. If your function is just reading an external array and not changing its contents, absolutely never pay the gas to copy it into memory. Leave it as calldata and reap all those efficiency benefits.
So once you've fixed the big structural issues, it's time to tighten up the nuts and bolts. Here are some rapid-fire micro-optimizations. Use immutable state variables for things that are only set once in the constructor. Mark any known compile time values as constant. Always limit your loop bounds safely so you don't accidentally iterate forever. And use smaller integer types, like uint32, where you are absolutely sure the values won't exceed the limit. These little tweaks tighten up the engine's performance without destroying our beautiful modular structure.
Okay, moving to Section 5, verifying the diagnostic report.
We're putting it back on the dyno.
Let's see how this builds. We need to rerun our local tests to prove to ourselves and to our users that our tune-up actually worked. Imagine we run our original, unoptimized baseline test. The scanner's needle spikes dangerously. Our batch increment function is costing a hypothetical, wildly expensive 50,000 gas per execution. That right there is a heavy, struggling engine.
But after applying our local memory accumulation, implementing our unchecked math trick, and keeping our arrays strictly as call data, we run the test again. Boom, 20,000 gas. That is a massive, tangible drop in gas consumption achieved simply by writing smarter code patterns. And this brilliantly illustrates the exact output you should be producing, your final debugging report. You map out your functions, log the baseline high gas cost, log the optimized low gas cost, and then clearly document the exact delta. This table right here is your proof. It shows that you aren't just writing code that functions, you are writing highly optimized, mathematically sound Web3 infrastructure. So that leaves us with one final provocative question. Are you ready to build efficiency directly into your function workflows from day one? Because instead of just patching things up after the fact, your next step is to write code that's testable and highly optimized right out of the gate. Thank you so much for tuning in. Remember, this explainer was proudly brought to you by Forge College. If you want to dive deeper into smart contract mechanics and really master other incredible Web3 topics, head directly over to forge.college. Keep building, keep optimizing, and I'll catch you next time.